I've kind of switched up this week. So in Neo, there's going to be some of these lecture notes. So I kind of want to just review the React lifecycle methods really briefly. And then we're going to do some hooks, and then we'll look at kind of some custom stuff. So let's just review though, and this is more just kind of getting these terms in our head and kind of these concepts of you know, the life cycle method. I just kind of really want to look at this this little diagram, and this really is for like this is specifically for class function flat class components, but functional components are going to be similar. So when we think about React components, we can kind of think about these three different like stages. There's like a mounting stage where like your component mounts to the DOM. And then there's like this updating phase where like maybe your state is changing or it's getting new props. So this can happen many times, this updating phase. This mounting just happens once, like that first, you know, when we do our use effect, you know, we mount our component. Updating is going to happen whenever we set the state or whenever that component gets new props. It's going to re-render the component, and that's going to update the DOM. And we haven't looked at this yet, but there's actually going to be a callback that we can do after something updates. So after our component updates, we can do a callback. You know, for a functional, for a class component, it's this method called component did update. For our functional components, we're actually going to use our use effect hook to do this. And then when we unmount a component, so you can think about like maybe you have like React router, or you're like toggling a component to show or hide. That component is going to like, you know, unmount from the DOM. And there's actually a callback we can call here called unmount, or component will unmount. With the functional component, it's going to be use effect. So if you thought use effect was confusing, now we're going to make it way more confusing today. Because use effect, if we're looking at a class component, these are broken up into their own methods. We have a component did mount, you know, where this is invoked immediately after the component is mounted. We have a component did update, and this is immediately invoked after updating occurs. And we can actually get access to the previous props and the previous state. And then we have component did update. Well, sorry, this is the same thing. So something about component did update, and this is going to be true with our use effect and just React components. What do you think happens? So remember, when I set state, that triggers a render, which updates the DOM and cause component did update. So if I call the set state function in my component did update, well, isn't that going to cause it to re-render, cause it to update the DOM, and cause component did update again? Well, then if I call set state in there, we're going to get into an infinite loop. So we need to be careful when we're using this component did update, and when we see the like the side version of use effect, that, you know, we're careful. It's not to say we can't set state in there, but we're going to need a little bit of a check. So we're not infinitely setting state. At a high level, do you see that infinite loop? If our component update, if we call set state in there, that triggers a render that updates the DOM, and we'll call component did update. There's our infinite loop. So we'll like look at like a little example with this as both a class and a functional component. I just kind of wanted to show this. I also want to show one other thing that's just kind of from Google. If I can find this image. So I'm just looking for, here's what I'm Googling. Has anyone heard the term, I know I've said it, but I heard the term recursion?
Only from you, I think.
There's like one good, okay. Here's a good definition of recursion. So here's the definition. Here's the word recursion. The definition is C recursion. Okay, so in coding, it's like it's a function that calls itself. Oh, now I'm seeing Zarding. Oh my gosh. So you kind of see this, like this is going to be an infinite loop because you're going to like, oh, what's the definition of a recursion? Oh, go see recursion. Okay, let's go look up recursion. What's that definition? Oh, see recursion, infinite loop. Because that's how a computer brain works. Just it's doing one thing at a time. It doesn't remember that it's in this function. So when you think about recursion, just think about this definition because this really defines a recursive function. And this can kind of go, it's not exactly the same, but calling something like set state, it's not directly recursion, but we're kind of causing this situation where we're calling a function that eventually will call component did update. So if we call a function that eventually calls component did update, we're going to get into an infinite loop. And I've seen this error twice in this cohort where people were getting stuck in an infinite loop in their React components because they were using the component. Like, let's say I had a list component, and then within that list component, I was using my list component. That is like going to cause an infinite loop because it's like using your definition in your definition. Does that, at a high level, does recursion now make sense?
Yeah, that makes sense.
I think that is like the best way to define it. But recursion is actually like a pretty common thing you'll see in coding, like recursive sorting algorithms. I know I think like merge sort is one. And so there's a lot of actually like this functions that call like themselves. There's a lot of recursive functions in coding that you use a lot. Let's just do merge sort JavaScript. I just want to see the code. Just give me the code. Merge. Don't explain it, just tell it to me. Okay, so here's a function, merge sort. Like this is the function name. So what we do is we divide the array in half. We just find that half point. And then something you need to have with recursive functions is something that's called a base case. Because if you don't have a base case, you're going to get into an infinite loop. So the base case is the way you prevent the infinite loop. So this is the way you can actually return from the function. So if the array.length is less than or equal to 1, this is where you actually just return. So how merge sort works is you take a list of numbers and you split it in half. And you keep splitting it in half until you have arrays of 1. And then when you have arrays of 1, those are sorted. And then you can like just sort them back together. But we won't get into that right now. But that is our base case. So we have a way out of this function. If our array is not, because this function takes an array. So if that is not length 1, then we move on. We split our array in half. We create a left and right array. And then we call merge and then merge sort, left and right. So what we do is we break this array into half and half and half and half until we break it down into an array of 1. Because if you have an array of one thing, that is sorted. That's ordered, like that's sorted. And then you can call this merge function that actually, it's a weird visualization. It kind of like you go down, you just break your array up into all these different arrays, and then you work back up to sort it. So, but this is a recursive function because here's my function merge sort, and now I'm calling it in the function itself, in the function definition itself. And this is actually like a very an efficient way to sort in an array. So let's do like a I think this is just kind of like can be a fun little example just to kind of, recursion is definitely a mind-bending concept. I think it's like, it's one of those things, once again, it's like simple, but it's not. The idea of it is really simple, but then when you try to understand like what's going on, it can get like downright confusing. So you can, I'll select this out and you can just maybe watch or you can follow along. But does anyone know what the Fibonacci sequences? Has anyone heard that?
I've heard,
Yeah.
but I don't know what the number actually is.
You've probably all seen this picture somewhere, right?
Yeah, don't you just keep adding the numbers together?
Yeah, so what you do is I've seen it start with like 0 or 1, but yeah, essentially what you do is how you get it's just a sequence. So sequences like have a pattern of how to get the next number. So this one, to get the next number, you add the 2 previous numbers. So if we start out with like 1, like 0 and 1, it'd be 0, 1, the next number would be 1. Then we add 1 and 1, that's 2. Then we add 1 and 2, that's 3. 2 and 3 is 5. 8 is by adding 3 and 5, so forth and so forth. And it's kind of this, like something you see like in nature all the time. like this is like, I feel like this is like an algebra thing. Like, I don't know. It's a very common like you see this in like hurricanes and galaxies and fruit. So it's and like when you split electrons. So it's a very common pattern you see in numbers. And then there's also something called the ratio. It like as you keep on doing this, you kind of, if you like divide these these two numbers, it's getting close to like this 1.68. So if that makes sense, like 144 divided by, or 233 divided by 144 is going to be close to this number. It's not going to be exact, but as you keep doing this, that's the number you're getting close to. So you'll see this number a lot. It's actually like, you'll see it a lot in coding. Like, there's a lot of math nerds in coding, and this is one of the most like famous sequences. So let's try to code this in JavaScript, and I'm going to do this with a recursive solution. Which is going to be a very horrible way to do it, but I'm just going to call this fib.js. So really how I figure out the number, if I want to like figure out the next number, and F is just like the sequence, Fibonacci. I grabbed that by, let's just call this N. So if I want to figure out the number, that's going to be like, I just take the, go back to, so take the number, like take the second to last number and then add, the first to last number. That's like how you write that mathematically. So, but let's kind of solve this in a like kind of think how you would think about this if you're doing like recursion. So I'm going to start defining like this constant function. Let's just call it fib. So this, how I want this to work is I give this a number. Like if I give this, 9, it's going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9. Should give me 34 because that's the 9th number in the Fibonacci sequence. Okay. So if I look at this, isn't really, I just really want to return, this is where I use the recursion part. I want to return the fib of num minus, we'll kind of follow up above from here, num minus 2 plus fib num minus 1. Right? If let's just say the numbers.
Wait, why are you minusing again?
Because, okay, so let's say I want to find 5. Or let's not do 5 because I think 5 actually met. Let's say I want to find, 13. And 13, okay, 1 and 13 is the 1, 2, 3, 4, 5, 6, 7. Is there one that has like the index with it? That would be maybe easier so I don't have to count this. Okay, here's one. So here's n. N's like the number of the sequence I want to get. So if I want to grab like the 6th, like the 6th index, that's going to be 8, right? Well, isn't that really just, n minus 2 the value of n minus 2, which is the fourth index, which is 3, plus n minus 1, which is 5, which is 5, which I take those together and I add them. Right? So if I look at like, what I'm trying to say here is like, let's say, you know, like fib of 6 should be 8, right? Fib of 6 is 8. Fib of 5 is 5, and fib of 4 is 3. So isn't any, like, if I did fib of, like, if I do 6 here, like I want to find the fib of 6, it's really just, you know, take this, find the 1, 2 back. So that would be 4 and 5. Like if I know the fib of 5 and I know the fib of 4, well, that's 3 and 5. That's going to be the fib of 6. Does that make, like, this is what this math is saying. Hey, take where n is, could say like n is like the nth term. You can almost think of it as like, you know, the index, even though it's not in an array, but it's like the index. We're starting at 1 and adding 1. So what's f, like the, if I go to 13, you know, that's going to be, you know, the fib of 11 plus the fib of 12. So it's 13 minus 2 plus 13 minus 12, which is going to be 89 plus 144. Does that kind of explain what this n minus 2 is doing right here?
Yeah, when you broke it down, it made more sense.
Okay. Now, if I call this right now, like, let's say I want to do like the fib of 6. What happens if I run this? I'm calling a function in my function. What error am I going to get? What happens like with that dictionary? If I tell my computer to, like, you know, if
Infinite loop.
yeah, that's an infinite loop. So I need a base case. Well, what's my base case? And I'm going to assume n is like, assume, you know, n is going to be greater than like 1. I'm not going to worry about 0. I'm just going to assume they're going to give me like 1. Assume n is greater than 1 all the time and is a number. So I'm not worried about like valid input. They're going to give me valid input. All right. So what is I kind of know if they give me n is 1, I know this value. I know if like n is 1, that the value's 1. So this is kind of like that weird thing with the array. It's like they go down until the array is, like, you have an array of 1, like one thing, and you're like, oh, that array is sorted. So that's like kind of your base case. It's like, hey, if n is 1, I know that's just 1. So I can do something like this. I might screw this up with like the off by 1, but like if num, or if n equals 1, or because they're also saying like 2 is 1. Let's see if, or is n equals 2, return 1. Okay, so let's try this. Let's do a console.log. And you know what, just for fun, I'm going to do a const count or let count right here. I'm going to keep track of how many times this was called. I'm just going to do a count plus. Like every time Fibonacci's every time this function's called, I'm going to add one to the count. So let's do fib of 1. And then let's run this node fib.js. Well, that works, right? That looks good. I feel like some of these, like you look at certain numbers, like I swear they like change if where you start at 1 or if you include 0. But anyway. And see, this one's good because you can kind of see how this ratio approaches 1.618. Anyway, so now I do fib of 2. And let's just also do like console.log count. So I do fib of 2, that was called 3 times. So my function works for 1 and 2. Let's actually do count down here. Just to show, okay, I'm not actually getting down here. We're returning here. So right now I'm not even going down here. Right? Any questions here with where we're at right now? This count is not needed. It's just going to be fun to kind of see how many times are we actually recalling this. So let's try 3. One, 1, 1, 2. Okay, that looks like that's working. Let's try 4. 1, 1, 1, 2, 3. Okay, that looks like that's working. Let's do 5. Actually, let's do this. Will be kind of interesting too. Let's do the count. So I'm gonna like right here, I'm going to just throw in the count. So we can see value is 1. And actually, you know, I'll just do it here so we can like, sorry, I'm switching this up. Okay, value is 1, count is 1. Just do these one at a time. And we'll do fib of 2, value 1, that one stays the same. Value is 1, count is 1. Let's do this one. Value is 2, count is 3. So these values are correct, right? That's the count is kind of just seeing how many times we're running this function. But the value is correct, so that's looking good. Okay, let's do this one. Value is 3, count is 5. Let's do our fib of 5. Value is 5, count is 9. Probably should just, guess let's do 6. So what should this value be? It's kind of making sure you kind of get, like, remember we take the last 2 values, add them up. This should be 8, right?
Yeah.
Okay. The count, like I'm not, like I don't know what the count is going to be. Probably, I don't know, like 20. I don't know. It's 15. But our value is 8. That's the important. So it looks like it's working, right? Isn't that kind of crazy? That's the code. And the logic is, hey, if it's one, if n is one or like, this is really the logic. It's just like, hey, if n is 1 or 2, return 1. If not, return the fib of n minus 2 plus fib of n minus 1. And we're doing recursion to solve that. And this looks like this is really clean, right? And like stupid clean. Almost. Might be confusing a little, but okay, so this one's like 15 and this is, oh wait, I already did that. Let's do 7. 13. I think this is kind of interesting to start like seeing what's happening to this count. Okay. Sorry, this is a little tedious, but this is going to be important. Okay. 21. That is 45.
41.
Oh, 41. Okay, 41. Thank you. Let's do 9. 34. 67.
34.
Oh my gosh, thank you. You're saving me. 34. That one's the important one. What's starting to happen? I don't know if you can quite see it yet with our count. What does, do you understand that what the count is like how many times we're calling this Fibonacci function?
It's about double what the value is.
Yeah, we're about,
Double minus 1.
yeah, almost, it's like kind of doubling.
It's double minus 1.
Or the count.
Yeah, the count's doubled the value minus 1.
I don't, it's not.
Like 55 plus 55 is 110, minus 1 is 109.
Oh, okay. I see what you're saying. Yeah, so we're doubling the count, but like relative to itself, like 1, 3, 5, like it's kind of growing really fast. But yeah, I see what you're saying. We're doubling the count minus 1. This is going to be let's start like doubling this by, because I'm pretty sure now we're looking like we went up to 10. Like like this is working. Let's just go up to like start counting by 2s. That's 144. That's 287. Let's go up to like, let's just do 15. We're gonna start counting a little more dramatically. That's 610. That is 1506. That's a little weird why that's like a weird coincidence that it was like doubled minus 1 there.
Yeah, up until the 144, and then 610 doesn't do that.
Yeah. But then let's go to like 20. Wait, that one does it, right? Oh, looks like it is. Let's go to 30. Let's just do 25. Let's count by 5s now. Oh, I need to, oh, that last one might have not done it because I had it. This one might be wrong. I'll put a star here. That one might be wrong. I might have not had comment out the other thing, which would break it. Yeah, it looks like it's continuing. All right, let's go to 30. I need to comment those out or that's gonna break it.
Yeah.
It's weird. Okay. There's a point to this. Let's go to 35. And then let's go to 40. I mean, did anyone see what happened there? Kind of starting, now we're really going to see it right here. Let's go to 45.
Is it because the numbers are getting too big?
It's the numbers are getting too big.
Yeah, because now they're the same.
Oh, I didn't, sorry, I didn't save that. I didn't save it. It's my error. Now I run it. Whoa, what's going on now? What is this count? This is as many times as we're incrementing this count every time we call this function. I've called this function when I did the fib of 45, it called that function 220 million times. It had to run this function, like literally it ran this function 220 million times. Like it hit this base case that many times. If I do 50, well now,
Takes a long time for that little hamster to do the math and bring it back.
well, yeah, I mean, you're asking it to do something like, 250 million times. And it's a function calls, are not like as far as they're not like the cheapest thing. I mean, there's a lot going on with the function call, like it throws it on the stack, there's quite a bit going on here. I mean, if you're doing 13,000, like this one just ran in an instant, right? It's very fast. We can do 13,000 or 150,000 calls. And, we didn't really start noticing, I'd say, the lag until maybe around 35 or 40. But now we're really starting to notice it. Like if I go up by 5, like if I increment this number by 5, it looks like it's needing to do 10 times as many function calls. That's just kind of like a little bit of a pattern I'm seeing, from 30 to 35, we go from, this is about a little more than 10 times as many function calls. That's about 10 times as many function calls. So if this pattern is holding, I'm going to expect this to almost be a billion,
It's
right?
still double -1. Just, I don't know why I didn't do it on your 610.
I think why I didn't do it on that one was because I had 2 of them running.
Oh,
So it's double -1. So it'd be whatever the next value is, which would be, I mean, we could actually figure this out. It'd be these 2 numbers added together, doubled -1. But it's still running. How long do you think this would take?
forever.
Yeah, you can like, I think pretty quickly you could like, I don't know what it's gonna be, but you could like get into like, because this is exponential growth of like this algorithm taking a long time. So if you get to like, I don't know which point, like maybe 400 or like 500, you could have the world's fastest supercomputer, like the fanciest computer, and it would take like the lifetime of the universe to evaluate this. And then let's say you make that computer twice as fancy and twice as fast. Well, all I need to do is just add one number. And now it's like that 2-time like improvement has just been wiped out. So this is a very bad, it's a good algorithm to show Fibonacci, but this is like, or to show recursion, but this is a very inefficient algorithm. Oh, there we go. What is that? 2.5. Oh, wait, no, that's more. That's 25 billion. I might have got that one wrong.
Hey, James, is there a way to set up a computer where it won't put itself in a situation like this, like it sees itself doing something like this, like a car, you can set it to where it won't go past a certain RPM so it doesn't blow itself up. But is there a way to, I don't know.
Yeah, that's what React does when it throws that error. It it says like, hey, you're in an infinite loop. We're like, if I were to get rid of this base case and run this, like it breaks. There's a natural mechanism in your computer where it breaks. And so what happens is, because that didn't take long to break, what happened is we reached this error. Maximum call stack size exceeded. So what happens for all these function, like when we do these function calls, like the first one we actually did does not finish. We called like the fib of like 50. And then it's like, oh, I need to do the fib of 49 and the fib of 48. And then the fib of 49 is like, I need to do the fib of 48 and the fib of 47. And these function calls all get placed on what's called the stack. And this is a physical thing on your computer. So it's not going to infinitely fill up, it's going to overflow. And you get a max call stack exceeded. Or you get a stack, like it's also called a stack overflow error. So that's where Stack Overflow gets its name, is this error. So there's the built-in way to not do that, and that is, your computer's just going to break. Cool. Or you could do something like React. React writes their language where they start to see it. And once they start to see it, they don't actually let you get to that point. React throws the error. Like, hey, you're probably in an infinite loop. We're going to break your app. You have an infinite loop going on somewhere. So that's what React does. But that's going to come in the form as an error. That's not going to be like a nice like it's going to be an error. Like your app's going to break. Cool.
Okay.
There we go. So there is recursion, calling a function within itself. If we use recursion, we always need base case, a way to exit. If you don't have this, that's, prevent infinite loop, like avoid infinite loop. which will manifest as a stack overflow error. Now you know the good old what stack overflow is, what that means in computer lingo. Another thing we're kind of just touching the surface of is we're looking at, because I'm just going to find one really quick and just actually I'm going to look for this article. There's a good article on this. Fibonacci JavaScript. Because let's do another implementation of this. So I'm just going to comment out this one. I'm just going to call this fib so I don't have to change the number. So this one implements it with a while loop. So it's kind of doing the same thing, kind of using the same logic, but just in a different way where, you know, we're going to start with A and B at 1 and 0. Those are like our starting points. I mean, maybe this should be 1 and 1. I don't know, but whatever. And what we do is we're going to, while the number, like we're going to start with like 50, and we're going to slowly start to like accumulate, like do the math and like add these numbers together. It's a slightly different way using a while loop, not recursion. And we're slowly starting to like build the sum up in B. And now this one, if I do like the log of fib of 50, you know, it does it fast. I can do like the fib of 500. You know, that's a huge number, but it's really quick. So we can have two different algorithms. You know, this one takes, you know, a fraction of a second, you know, for big numbers. You know, and this one takes, you know, lifetime of universe. Big numbers. So as you're starting to code, it's really not like you really don't want to worry about efficiency. You know, you're kind of just like it's, and even if you're not like, even if you are like an experienced coder, like there is kind of like this general rule. It's like, you know, you kind of get your code working first. You don't really try to make this more efficient, especially if it's like you're comparing like, oh, this one takes, you know, 1/1,000,000th of a second versus 2/1,000,000ths of a second. It's like, who cares? But, you know, obviously we can run into where like we do want to concern ourselves with efficiency, because this is a pretty big difference, right? I mean, haha, like this is like one of these takes forever, the other takes like no time at all. So when we start to think about algorithms and their complexity, there's something called big O notation. And we're not going to go into this in this course. I want to throw out the term. I want to throw out what it is. And it's going to be something I recommend that after this course, you know, it's something, one of those things you could go look at. You go do like an algorithms and data structure class. Like, even if it's just like a quick one on Udemy, because you kind of talk about this stuff and you kind of look at different algorithms. So with this, and I'm going to throw this out in Slack. I think this is like, you know, an article you should read. You know, it's like a 3-minute read. But what big O notation is, it's just a way to for like coders to describe the efficiency of algorithms in like a simple way, like in a more like big picture way. It's like I don't really care like if it's like fractions of a second quicker. I really care if it's like, is it life of the universe versus milliseconds quick. So big O notation gives us a way to describe algorithms in a mathematical way. Like, how efficient is this? So what you'll see here is this graph right here. This is like thinking about like on the bottom is going to be like your elements. So a very clear case we could use this for is like, for our fib, it's like, how high do we want to go up to find this number? And we could have different algorithms that find that differently. Like our algorithm, the recursive one, I think it's an n squared, or it's either, I can't remember, it's a 2 to the n or n squared. I think it's 2 to the n, which is, I mean, it's definitely 2 to the n. So it's like as our number grows, like our algorithms like exponentially growing, even worse than n squared. So it's this orange line. And you can see as we start to go up in numbers, like the operations we have to do is just growing exponentially. And we saw that like once we got to like 50, or even I think it was 45 or 50, we were doing like 25 billion operations. So as our number grows, like, the amount of operations we are doing is exponential. But then we could have another algorithm like this one, where it really just depends on the size of n. Like because this is just what we're just doing a while loop, like pretty much num times. So that would be like we would call that O of n. Like we're just doing the operation. Like if I tell you to find out the Fibonacci of like 1,000, then you have to do 1,000 operations. And then we get this nice green line. And O of n operations are like, nice. There's also like an O of log n operation. That's that red line. Those are very nice. And O of 1 is the best. What would O of 1 be? That's just 1. It just takes one operation to do the thing. Let's kind of see, like, I think this log of n can maybe be a little confusing. Let's look at an example of what might be a example of that. So when you're talking about like these algorithms, arrays are kind of a good way to like think about them, where n is going to be the length of the array. Okay, so let's say I have an array of like 10-ish things. So I could ask, like, if I want to find something, if I want to find by index, like let's just say find by index. So here we have my array, let ARR or equal that. How many operations do you think this takes? Just go in and like find an index.
1.
Yeah, that if we're using our big O notation, that'd be O of 1. Doesn't matter how big my array is, I can just go in and access it. So so accessing a item in an array is like extremely efficient. All right. So that is like Yay, the best. Like you don't get faster. So we'll just say accessing by index. All right, let's do something else. Let's say I want to, and I'm going to throw this up here. Let's say I want to find a number. Let's just say we have a find method. I want to find 1. Oh my gosh, why does it keep doing that? Find. How many operations is this going to take? Like I want to find the index.
One.
And maybe let me make this so we're not getting confused with the index and the number. I'm just going to add 0 to all of these. So I want to find 10. Yeah, you said 1. So maybe, yeah, in this particular case, that might be 1. What if I want to find 99? How many operations is that going to take? Like, what do I have to do if I want to find a number in an array if I'm a computer? I have to go through each number and see, hey, is this the number? Like a computer doesn't know the numbers in the array. So if I want to go find 10, I just go start looking for 10. I'm like, oh, there it is. Okay, that took 1 operation. What happens if I want to find 99? Like, what do you do to find 99? Like, what are you doing right now in your brain?
Looking at each number and seeing if it's 99.
Yeah, you go through, you look at each number. It's so, and 99 is not in there, right? So that is going to be, so finding is really, you know, we could say, hey, like best case is 1, you know, worst case is n, average case is maybe n divided by 2 if the thing's in the array. But you know, we're just going to go with n because we don't really care if it's n divided by 2 or n. It's just n. So to find something, we're going to say it's n. It's where n is the length of the array. Does that make sense? If I want to find something, this is going to be an n order operation because I have to look. I just assuming I'm going to have to look at everything. I might find it on my first shot. I might find it here, but something with big O notation, we don't really care if it's like n divided by 2. We just ignore that divided by 2 and just say it's n. Does that make sense? Yay, nay?
Yeah. I believe so.
What would happen if this array was sorted? And I want to find something. Is that going to change the efficiency, or can I think of a different way to find a number?
Index?
Not, I mean, index is not going to work because I want to find, let's say I want to find 99 still. I can't, I don't know.
Yeah,
But how does it being sorted? How might that help us?
I mean, like as a person looking at it, you know where it might be in relation to everything else.
Yeah, exactly. You kind of can like zoom in and maybe like find an area. a computer can't, I mean, can't do that directly, but what do you think we could do, or what's one way we could maybe do this with a computer? I'll just kind of,
Is this where you could maybe split it? And so you know which half of the array it's on?
yeah, that's kind of like, that is the idea. What I'm going to do is I'm going to find the middle, like as the computer, because a computer can't really look at these different numbers at the same time. It can only look at one number at one time and compare one number at one time. But what I could do as a computer is I could find the middle number in my array, and I could ask, is that number equal to 99? All right, so I go, hey, I go find the middle number, which is, let's just say is 60. And I say, hey, is that equal to 99? No, it's not. But I can also then ask, okay, it's not the number, awesome. Well, is it greater than or less than? I'd be like, well, 60 is less than 99. So you know what? After that, I know I don't need to look at any of those values on the left side of that 60. And then I can do the process again. I can go find the middle thing. Let's just say it's 800. I mean, it's either going to be one of these two. And then I can say, hey, is 899? No, it's not. Okay, well, is 800 greater than or less than 99? I'm like, oh, it's greater than. So then I can say, hey, I don't need to look at any of those values to the right. And now I'm down to 1. And then I can say, hey, is 99 700? No, it's not. Okay, well, it's not in the array. So this is the, if array is sorted. Now this is kind of do you see how this is like the opposite of like exponential growth? If I'm looking at something, I can like break stuff in halves, because I can look in the middle of the array and like choose half of the array to get rid of. So I'm like dividing things by half. Does anyone know what like math operation that is? Or it's not division, or like what kind of like the graph that's what do you say?
Median?
Medium?
Median?
No, it creates like an exponential graph would like, be that whoop. Where this one's kind of going to be like the opposite, where it goes like levels off, like it goes whoop, and it kind of it has that little curve, but then it goes whoop. It's kind of like the reverse of an exponential. This is your log. And these are going to be like base 2. It's like log base 2 of your number. And these are like, this is, so we'd say this operation is O log of n. We take the log of n, it's going to be log base 2. Which, I mean, so let's say we had like a thing of like 1 million items, like an array of 1 million items, and it's sorted. Like that's going to be the log of 1 million. Does anyone know around like how many things are we going to have to look at? Like how many times are we going to have to split that array in half to see if the item's there or not? Like I don't know what the log of 1 million is, but it's probably like 18. You could ask the question like 2 to the what is 1 million? That's like what a log is. So log n operations are really efficient. And we can see this right here, this log of n. It is essentially like, it's pretty much as good as like a one operation. If you can get a log n operation, that is, you know, the next best thing. You can also get these like n log n operations. So it's like n times the log of n. Those are decent. So. And like array sorting algorithms, where you can like really, there's like a good website that like visualizes all these. Okay, you have, okay. So there's all these different like sorting algorithms, like how many different ways can you sort in an array? So there's like all these different algorithms that can do it. There's all these different use cases. Like, is it a random array? Is it almost sorted? Is it reversed? Is it all few unique? So you can go through and like see which ones are more efficient in which case. And then there's always just some that are like horrible. So there you go. There's data, there's like data structures and algorithms in like 30 minutes. And recursion. So let me Slack this out too. Cool. Is that interesting to anyone?
Yeah, it's definitely interesting. That's
So this is the stuff you'll learn in like data structures and algorithms. You'll go learn how to write some of these algorithms. Like you'll probably never need to write these algorithms because they were like developed, you know, quite a while ago. And let's do like, let's also, let me throw this one out as well. There you go, notation, cheat sheet. This one's a pretty good one. So yeah, here's kind of showing like the complexity. So any of these like O to the n, like O to the n factorial, that's yeah, horrible. Like O to the 2n, these are bad. You know, some of these are good, some of these are, you know, great. And then you can go look at your data structure and you can go see, you know, what the efficiency of these can be. So like to access in an array is O of 1, to search an array is O of n, to insert into an array is O of n. You know, and then you can look at all like these like ways to like search and sort. They've all like figured out like the best average worst case for all of these. So there are just some algorithms that like, you just can't write them better than some of these. Like some of them are just inherently like 2 to the n like 2 to the n algorithms. Like all of the algorithms that like handle like encryption and like all of our security, those algorithms are all very like 2 to the n. Like you want those to be 2 to the n, and you don't want there to be a way for them ever to be like n log of n. Like you can't write those algorithms efficiently. So that makes them secure because they're not solvable unless you have like a quantum computer. But anyway. So look at this. I think that this can, well, you don't, I mean, I just kind of want to show this to you. It's not like, probably won't go into it much more. But I think it's something as you get more comfortable with coding, something like it can be an interesting thing to learn about in like a more, like a course that's, it would be called like data structures and algorithms. That's like the course you would learn about this kind of stuff. So, and if you're like applying at Google or like a major tech company as a software engineer, you would like need to know this. So, because this might be part of their interview questions is to like, you explain this stuff. But most like web development jobs don't care. Sweet. Yeah, let's take a break. Let's come back. Let's just call it 11.
All right, sounds good.